Greetings, Matt Roscoe here at the University of Montana in a short lecture on section 3.4 from our text, The Product and Quotient Rules for Math 570 Calculus for Middle School Teachers. Okay, I want to do an initial investigation, then we'll formalize the product rule, and then we'll use the product rule to show, to find a rule for quotients, and then go through some examples. Okay, so the initial investigation I want to do is to investigate the derivative of the following function where h of x is equal to x squared times x. So let's go ahead and fire up the ElmoCam and talk a little bit about that particular function. Okay, let's see, move this out of the way. So if h of x is equal to x squared times x, the first thing you should be thinking to yourself is, well, I know what this is, right? H of x is the same thing as x squared times x is x to the third, and so h prime of x should be the derivative of x to the third, which we know from the power rule is 3x squared. So we should, intuitively know right away that the derivative of that function is this, because we're allowed to algebraically simplify or rewrite this in an equivalent form, and one that's more convenient perhaps for taking a derivative in this case. But let's think about the point of this, I guess, is for you to think about, well, how could we generate some sort of rule where we can kind of think about products, where we have functions written as products. And, this might be a polynomial, and this might be, say an exponential function, or this might be, some logarithmic function, and, this might be a linear function. So, in this setting where we can't combine things, what do we do when we have a product of two functions is what we're trying to get at. So if I call this one f of x and this one g of x, then the first thing you should notice is that f prime of x is equal to 2x, and g prime of x is equal to 1. So right away, one thing that you can notice is that the derivative of a product of two functions is certainly not equal to the product of the derivatives, because the two derivatives, when we multiply them, you get 2x, and 2x isn't equal to 3x squared, which is what we believe this to be. So right away, there's some interesting thing going on there. Let's write down what f of x is. It's equal to x squared, and let's write down what g of x is. G of x is equal to x. So if we want 3x squared, and we kind of probably have this intuition that it has something to do with these four things, because after all, that's really all we have at this point is we have a function, and both of their derivatives that we think would play a role in some rule. But the rule we're looking for is the one that arrives at 3x squared when we combine these four elements. And of course, there are quite a few different ways we could combine them. And the question is what's the right way? And the right way, it turns out, is, perhaps you can see it, is that if you combine this function with that function and get a product, you'll get x squared. And if you combine this function with that function, or you take their product, you'll get 2x squared. And an x squared plus 2x squared gives you a 3x squared. And so it appears that there's some sort of a mismatching, or I guess a cross-matching of function times the other function's derivative plus function times the other function's derivative. And indeed, that turns out to be the product rule. That h prime of x in this case, and in all cases where we have two functions being multiplied, if h of x is written as some f of x times g of x, then h prime of x will be f of x times g prime of x plus f prime of x times g of x. So sometimes we hear this said, the first times the derivative of the second plus the second times the derivative of the first. So derivative of the first times second. And just to make sure you're clear, that in this case is equal to, well, f of x is x squared, right? Times the derivative of the second is 1, so the derivative of the second function is 1, plus f prime of x, so the derivative of the first function, that's 2x, times the second function, which is x. So what do we get there? We get x squared plus 2x squared, which is equal to 3x squared, which is correctly equal to the derivative. So obviously this is just a one-case proof and one example. It's not a rigid proof or rigorous proof. If you're desiring a rigorous proof, you can certainly see that in the back of the chapter on the focus on theory. But for now, we're going to go ahead in this much more applied course and accept this as good intuition and go ahead and present to you the product rule. So if we have f and g as both differentiable, then the derivative of the product of the two functions f and g is equal to the first times the derivative of the second plus the second times the derivative of the first here. Or you could write it as the derivative of the product f and g, functions f and g, is f times g prime plus f prime times g. Okay, so it turns out that there is a rule as well for quotients, and this rule is a little bit more involved. But notice that it's very similar to the rule we just took a look at. Instead of a product of two functions, here you have a quotient of two functions, one function being divided by the other. And it turns out that it's the bottom function times the derivative of the top minus the top function times the derivative of the bottom all over the bottom function squared, no derivative down there. Or if we just write them without the x's and use Newtonian notation, we could write it as f over g prime is equal to f prime times g minus f times g prime all over g squared. So there is kind of a cute, neat way that you can prove this to be the case by using the product rule. And I'll just run through that with you now, just to give you a sense that this does come from someplace. So one way we could think of this is we could think of the two functions as so f of x all over g of x. If we want to think of this as d by dx of this whole thing, we could argue, well, this is really just a product. It's d by dx of f of x times g of x raised to the negative 1. And that's a product, right? We have a function times another function, so we can apply the product rule. So I'll go down here. So the product rule, which we just proved, says take the first times the derivative of the second, so it'll be f of x times d by dx of g of x. And I guess I want to do raised to the negative 1, but we'll use big brackets there. First times the derivative of the second plus the second, so it'll be 1 over g of x. So I don't know, we'll just call that g of x to the negative 1 times the derivative of the first, so the d by dx of f of x. Sorry, I'm kind of going off the screen there, or the board. So let's think about that. So what's going to happen here? Here we'll have f of x times, just if you have any intuition right here, you should think about it. You know, what's going on? I'm taking the derivative of a function that's inside another function, right? So the chain rule applies here. So f of x would be equal to, or the derivative of g of x to the negative 1 would be the same thing as the derivative of the outside. So negative 1 times g of x to the negative 2 times the derivative of the inside, and the derivative of g of x is just g prime of x. And here what I have is g of x to the negative 1 times the derivative of f of x. Well, g of x to the negative 1 is just a g of x down below, and the derivative of f of x is just f prime of x. Okay, so we've got one quotient over here, and that's looking good. It's got a g of x in the basement down there. We would expect that to be squared in the final answer. But here I notice that I've got a g of x to the negative 2. I've got a negative 1 out in front of it, f of x times g of x. So it looks like on top what I have is f of x times g prime of x. And on bottom what I have is g of x. But I have a negative 1 from the chain rule resulting from the negative exponent on g of x. So this is what I have for this term, and this is what I have for the second term. I guess second quotient. And it appears that, oh, I missed a square there because this is to the negative 2 power. So it appears that I need a common denominator, and the way I could get that really quickly is just to multiply by g of x top and bottom. And when I do that, I get a g of x squared on bottom, and I get on top an f prime times g of x minus an f times g prime of x. So I'm going to write these, I'm going to commute the addition and write this term first, and what we'll get is f prime of x g of x all over g of x squared. Oh, sorry, we're putting it all over a single g of x squared since we've got a common denominator. And then I take minus f of x times g prime of x. And that indeed is the quotient rule, the rule that's displayed there over on that other side of the screen. So so you can see that there are some nice algebraic sort of tricks that you can do to use the product rule to lead us to the quotient rule. The trick, of course, being rewriting g of x as g of x raised to the negative 1 and then incorporating the chain rule in the derivative. So kind of a nice result. I hope that you like that, and that gives you some, I guess, confidence that the rule is indeed true. And if we assume that the product rule is true, then certainly we haven't broken any rules here, so the quotient rule must be true as well. All right, well, let's get to some examples. So let's take a look at differentiating some functions that are products and quotients. So let's take a look first at number 1. F of x is equal to 2x over x squared plus 2x. So f prime of x is going to be, this is a quotient, right? And so we kind of think of this as the top function and the bottom function. So how would we do this? Well, there's some labeling issues here, right? Because in the quotient rule we have an f and a g, the f playing the top function and g playing the bottom. But if we paste this, you know, with a, let's say this is g of x and this one is h of x, then we can kind of, you know, relabel what our derivative should be. So in your mind, what you should be thinking is, okay, it's a quotient function, so it's the bottom times the derivative of the top, so it's h of x times g prime of x minus the top, g of x times the derivative of the bottom, h prime of x, all over the bottom one squared, so h of x quantity squared. So that's what the quotient rule would say if we had h's and g's when f, for example, is taken up in the labeling system adopted. So let's go ahead and do this. So the first thing we do is take the bottom, so it's x squared plus 2x times the derivative of the top, and the derivative of the top is just a 2. And then we subtract from there the top, which is just 2x, times the derivative of the bottom. Here we'll have 2x plus 2. And then that's all over the bottom squared, x squared plus 2x quantity squared. And this is the derivative. Now from here on out, it's just algebraic simplification to get to an answer that you feel is palatable for the audience, that you are trying to present to. So in this case, let's go ahead and distribute both of these products on top and just see if we can get some things to combine. So it looks like it'll be 2x squared plus 4x, and it'll be minus 4x squared minus 4x, and that's all over x squared plus 2x quantity squared. So what I do notice is we do get some cancellation. The 4x and the minus 4x go away, and I have a 2x squared minus a 4x squared, so it looks like it'll be a minus 2x squared on top. And on bottom, I will just have x squared plus 2x quantity squared. It looks like an x squared on top might cancel with one of the x's down below if we pulled it out. I'll leave that to the further simplification if you'd like, but at this point we've definitely demonstrated the role of the quotient rule in obtaining at least an answer that's on its way to simplest form. Let's go ahead and move on and take a look at another example. How about e to the x times x to the third? And we're going to call this one g of x, right? So again, the labeling convention has gotten in the way. G of x is in the actual statement that we gave earlier, the product rule. So let's call this, I don't know, h of x, I don't know, j of x. So we have some product here that we can kind of think of this one playing the role of h of x and this one playing the role of g of x. And so we know that if we're looking at it from that standpoint, g prime of x is going to be the first times the derivative of the second. So h of x times j prime of x plus the second times the derivative of the first, j prime of x, oops, no prime, second times the derivative of the first, h prime of x. So that's the product rule at play. So we'll go ahead and let it play out. So if we have h of x equal to e to the x, I just copy that, and j of x equal to x to the third, j prime of x then will be 3x squareds. And then on the second one, we'd have x to the third times h prime of x, and h is e to the x, so its derivative is just itself, e to the x. And so this would be the derivative that we get. I can see that I've got two terms being separated by an addition sign, and so I should probably think, is there anything I could bring out in front of the two terms? And it appears that x squared is common to both and e to the x is common to both, so I'll take both x squared and e to the x out. And when I do that, I'm left with just a 3 here, and then here, if I take an x squared out, I'm left with an x. So it looks like that would be one acceptable way to write this. It's x squared times e to the x times 3 plus x as our derivative. Again, graphs of these should be interesting to look at because the graph of this function should tell you the slope of that function at any point. I encourage you to use technology to perhaps check your answers if you're uncertain. Okay, the next one is h of x is equal to e to the x over x squared. So we have this function. We can now use our naming convention just like this one is f of x, and this one we'll call g of x. So if we think of h of x as some f of x over g of x, then the quotient rule applies for its derivative. It's the bottom times the derivative of the top, so it should be g of x times f prime of x minus the top times the derivative of the bottom, f of x times g prime of x, all over the bottom one squared. So there it is, the quotient rule. Let's go ahead and fill it in. So we would have g of x, x squared, times f prime of x, e to the x, minus f of x, e to the x, times g prime of x, 2x, all over x squared squared. So now again, it's just a simplification problem. I see that there's an x and e to the x in both of the two terms on top, so I'll factor that out. X e to the x. What I'm left with is an x minus 2. And then on bottom, if I take x squared and raise it to the second power, I get x to the fourth. And now, since the x is out in front of the product here and here, I can factor it out and cancel it as a 1. So we can take 1x away from the top and the bottom, and we'll get e to the x times x minus 2 all over x to the third as our answer. Okay, again, I would encourage you to take a look at this graph and the graph of this particular function, and ensure that the graph of the derivative indeed describes the slope of the function at every point. I'll go ahead and move on to the next one. J of x is equal to 3x squared times x minus 4. Well, I know what you're thinking. You're thinking right away, why don't you just distribute that and treat it like a polynomial? But let's play the game. Let's call this f of x, and this g of x will compute its derivative and then check it using the polynomial expansion. So what would j prime of x be? Well, it looks like what we have here is a product of two functions, so we're going to use the product rule. It's the first times the derivative of the second plus the second times the derivative of the first. So we'll go ahead and compute that now. So the first is 3x squared. The derivative of the second, well, the derivative of x is just a 1. The derivative of the constant is 0, so we have just a 1 there. And then plus, let's see, g of x is x minus 4. And the derivative of the first is 3 times 2 is 6x. And now it's just a simplification problem. We have 3x squared here. Plus, let's see, 6x distributed across the binomial would be 6x squared minus 24x. So it looks like we have common terms here, like terms sometimes called, 9x squared minus 24x. And you could simplify however you'd like, but let's go ahead and see if this actually checks out. So here's our check, right? We said at the beginning, well, we could rewrite this thing as just 3x squared distributed across the binomial up there. Sorry, I'm getting a little off the screen. It looks like that would be 3x to the third minus 3 times 4 is 12x squared. And so j prime of x would be just using the rules we know that apply to polynomials. First, the power rule on this particular one, 9x squared, and then the power rule on this particular one, 12 times 2, 24x. And sure enough, that does check out to be the same. So that's it for the product and quotient rule. I look forward to your questions, and let me know if you have any.